Hello and welcome to this second video about AKDL. You remember last time we have defined numeric expression like this, and well, I changed it a little bit because in this video we will see how AKDL can generate an evaluator also for you. So let's go back to our project. Here, last time we had our code generated and we had to evaluate it by ourselves, like here we call the evaluate method, and the evaluate method will instantiate the main parser and go through the generated runtime code by getting the expression and calling evaluate expression and so on. And at the end we had our result. Right now we don't want to do that, so we start anew from scratch, and here we just don't do anything. So if I run that, I will see my expressions and no value calculated here. What we want to do is, instead of calling this evaluate method, just calling an evaluate generated by AKDL. So I will delete all that, maybe that also, and back to here. So here we say I assign a numeric evaluator to this. And in fact, that's it. The whole structure is assigned as being a numeric. What we have to do more is to recognize that our operators are in fact operators, because the difference between just a keyword and an operator is that the operator is considered as a function. We'll see that more in details afterwards. So I just have to check the places where the tool detects probably that could be an operator. For example, assign here. Everywhere where I have an enum, the keyword above may be an operator, and it is. Here we have no, I added also some new elements to my factor. For example, here a factor can be a sign, plus or minus, followed by another factor. It can be a number, it can be a variable, and a variable is an identifier with a value which will be a field generated in the runtime class of type double here, and here this checkbox runtime reference says this field will be generated to the runtime code, but doesn't have any incidence on the parsing. And as this key has those two elements, it is proposed to be marked for initialization. Of course, a variable has to be initialized before we evaluate it. So I mark it. And optionally, we have added some new stuff here and there. A keyword exponent, which is a new operator, root or power. Well, I've chosen those two signs to say power here and root there. Maybe, well, I'm not very happy with this sign, but that's the only one I've found which could be good enough. So I will say this is also an operator, and having done that, I can generate my code. And here it is. We turn back to our project, refresh that, and here it is. So our entry point is numeric here. Do that. Create an eval method here, which will return a double. Double. And here I will instantiate my numeric parser and parse equals new with a new string reader. I give the argument, and now if and parse could parse, I will return and parse get numeric runtime, get expression, evaluate. So that's it. If we run that, we get our result. So the evaluation is made by the generated code itself. So what's in it? We can have a look. Our expression has implemented this evaluate method, which works on the stack. We declared a stack here. We initialize the stack first, and then we traverse the whole instances of the runtime. We gather the information on this stack, and then we resolve the objects by getting those information from the stack. And at the end, what's left on the stack is the result. So that's what we return. Resolving the elements here mean to look for the operators we declared. So here we recognize add, sub, mul, div, minus, and power and root. So that's what I give to you as standard. And if you need some more operators, you can implement them by yourself and register your evaluator within this user exit handler, and in that way I will call this method resolve, which you will implement. We will see that afterwards. So if we go one step beyond, we turn back to our AKDL, and I will choose this expression. Here I have defined some more expressions. So I gathered all the kinds of expressions we may have. Here are the numeric expressions. I have marked them already with this evaluator. So there are three kinds of evaluators. Here is the numeric evaluator. This one is a logical one. And the last is a custom evaluator. So numeric evaluator is what we've already seen. Logic evaluator is something quite similar, but operating on logic, so binary elements, like the logic operator is OR, NOR, XOR, XNOR, and the logic factor operator here we have a NOT. Here is the factor operator, and here we have AND and NAND. So of course, if you don't give any value, the name will be the one which is taken in account. So that's something you have to know. Well, I will generate this code. And here we have some more stuff. Turning back to our project, we refreshed it, and here it is. Here we consider the complete example, which is has much more code as the previous one. We have an input file here with some markers here telling, for example, for this one, what follows will be considered as numeric expression. So all that is numeric. Here we see our signs. This means power 2, so it's square, 3 times 4 squared, and this one is a square root. So square root of this addition. Here we have then an equation of second degree to solve. We have coefficients a, b, c given here, once, and the second time another one. After that we will evaluate a logical expression like this or that, and at the end we have a regular expression. So in this example we will not evaluate, but just interpret that and tell what's the meaning of this regular expression. So here is the code for that. So we will read this input file, and if we find something in that begins with this sign, we will just get the type of the expression we have. So the type is given here in an NU, either numeric or equation or logic or regular, and we will dispatch then according to this type to the appropriate methods. So here we have our numeric expression. Here we will solve the equation and then evaluate the logical expression and the regular expression. Well, for the numeric, it's already something what we have seen. This time we see our partial parsing. So the main entry point is expressions. If we turn back to our definition, we have expressions as entry point, and here we have our three types of expressions, and we will consider them as partial parsing. So that means we generate the first one, which is the numeric expression, and we parse our argument given to the entry point from this expression. So that's the way to do it. So this one is an expression, numeric expression. We will parse that, giving as argument this one, the entry point, and telling here it's not optional. And after that's done, we just call get expression. That's our runtime instance, and we evaluate it, and we have the result. In this solve equation, we have some more stuff to do. First of all, we want to, well, here we have a kind of parsing to get the values A, B, C given here. So I just use split and I get my ABCs, and I pass that to a class that I have to show you here. This class implements something I generated. So this generated code is here under com run num expression. So that's all what was generated. We have an evaluator, we have this expression user exit and expression user exit handler. The handler is just a singleton where we can register a user exit from the customer. That's this one. So this one I have to register it. It will be from this type. So we find that here, and here is my registered user exit, and I will use that to get the value of a variable. So I just call u to give me the value of the object. Okay, and the other way we use this user exit is we will see that later on. So right now we have then created this instance, which will put these three values into a hash table, and at the moment you call me here to get the value of the object, I will check if this object is a variable. If it is, I look for the name of this variable. If it is A, I will get back the value of A I stored here. If it is B, I will get back B and C the same. Okay, so that's it here. Then we will parse this. That is the, so to say, the beginning of the solving of this equation. We have to calculate delta, which is b square minus 3 times a times c. I give that here to my expressions entry point, and then I will parse that. And once it's parsed, I get the result here. I write this result on the console, and then I ask if it is greater than 0, then I do the following. If it is 0, I have only one result. x1 is equals x2 equals this. I don't have to do much more. If it is less than 0, there is no real result. So here is the interesting point. The next step is to calculate x1. x1 is minus b minus square root of delta divided by 2 divided by a. And I do the same here. Evaluate gives me the result. And x2 is the same with a plus sign here. Here I changed a little bit my expression. It's the same, but it's to show that it also understands this kind of expression. Okay, and for the logical expression we do similar things. Here we register also a user exit where we give the values A, B, C, D, and here in this second part we change the values of A, B, C, D, and we call the evaluate again, and sometimes we get some different result. And here we do the same, but we have a customer user exit, like here, but this one does much more than the other one, because all the interpretation is made here. So you are the one who can interpret your code, so to say. What is given here is the traversal of, like in the other cases, the traversal of your runtime. The result will be gathered in the stack, and you get the stack and you interpret it. So here you go through the whole stack objects, and if you recognize some elements that are relevant for you, you do your interpretation. So that's an alternative to traversing the code by yourself. So if you want, we can see again what happens here. Evaluate. We will clear our stack. We will traverse the runtime. That means each element of the runtime will be called if needed, and the concrete traversal will lead to push values on the stack. And at the end, you will be called by this method if you have registered it. So if we run that, we will see the results. So here we have the same as in the first example. Here it begins to be more interesting, because we have the square and square root. Here also a bit complicated, more complicated. And here we have our equation. We have delta and x1, x2 values, so we can check the result is correct. After that we have our logical expressions, and here are the regular expression meanings. So that's it for this video, and I hope you enjoyed that. You can still find in the description of the video the links to the GitHub of the project you can download, and see you next time for the next video. Thanks, bye bye.